Hey everyone, welcome back to my channel. In this video, we're kicking off our CCNA Lab series, and today's focus is on implementing VLANs. We'll dive deep into VLAN configurations, access ports, VTP and DTP, the native VLAN, and more. By the end of this video, you'll be able to configure VLANs on multiple switches, set up trunk ports, and understand how VLANs work in a network environment. Before we dive deep into VLANs, let's take a look at this basic LAN topology here. As you can see, we have a single switch with some PCs attached to it. To help understand the concepts of VLANs, a LAN includes all devices in the same broadcast domain. So in this kind of topology, assuming no VLANs are configured, this is considered as one broadcast domain. A broadcast domain is a part of the network where a broadcast can be received. So for example, if a broadcast packet gets sent out on this network, all hosts will receive and process that broadcast packet. So in a way, you can think of a LAN and a broadcast domain as the same thing. A switch can have some interfaces be configured in one broadcast domain and other interfaces be configured in another. These broadcast domains created by the switch and configured by the engineer are known as VLANs, or virtual local area networks. So why VLANs? Having all devices connected to a switch with zero configurations on it can cause a great deal of overhead and congestion on the network because all devices will be within the same broadcast domain. Segregating the networks by dividing hosts into different VLANs and subnets will reduce the amount of congestion on the network. Furthermore, by implementing VLANs, we can limit the number of hosts that receive a single broadcast frame, which is helpful because this can reduce the number of hosts that waste effort processing unneeded broadcast frames. VLANs by default cannot communicate with each other. So devices configured in VLAN 10 will not be able to communicate with devices that are configured in VLAN 20. So with that, introduces a form of security. However, there are instances where you would want VLANs to communicate. That can be accomplished through inter-VLAN routing, which is a topic we will cover in another video. Let's take a look at another topology, but in this topology, we have two switches. These two switches have some PCs attached to them, as well as a link between the two switches. It is always good practice to use a crossover cable when connecting similar devices, such as a switch to a switch, router to router, PC to PC, PC to router, etc. Even though these devices will most likely use auto MDIX, it is always useful to know when to use a crossover cable. And right now, with no configurations added to these switches, these computers will be able to communicate with each other as long as their IP parameters match, because every switch port belongs to the default VLAN of VLAN 1. Now, we cannot change or delete the default VLAN, and the default VLAN will always be VLAN 1. So right now we have these computers attached to switch 1, and I've added IP configurations to these computers to show that if I issue pings between these two computers, they will be able to communicate with each other because they all are in the same VLAN in the same subnet. So I will ping PC6 from PC1. And as you can see, the pings succeed because, again, they are in the same VLAN and in the same subnet. So going back as to why we use VLANs, we want to reduce the amount of devices processing unwanted broadcast frames and improve security and performance by offering network segmentation. And having our network set up like this does not accomplish these goals. And to do this, we must configure VLANs on our network here. In our topology now, I grouped PCs 1 through 4 into VLAN 10 at the top that reside in network 192.168.1.0 with a 24-bit mask, and PCs 5 through 8 into VLAN 20 at the bottom that reside in network 192.168.2.0 with a 24-bit mask. On switch 1, I have PC1 connected to switch port fast Ethernet 0/1 or F0/1 for short, PC2 connected to F0/2, PC5 connected to F0/3, PC6 connected to F0/4, and going over to switch 2, I have PC3 connected to F0/1, PC4 connected to F0/2, PC7 connected to F0/3, and PC8 connected to F0/4. On each switch, we must configure a VLAN 10 and a VLAN 20 and assign each switch port to be associated with the correct VLAN according to this topology here. Now, let's go ahead and configure these switches. We'll start with switch 1. Click on switch 1, and at the top, the third option, you're going to want to select CLI. And now we are in switch 1's command line interface. This is where we're going to be executing all of our commands. Now what you're going to want to do is press enter, and you'll see that we're prompted with switch and then a greater than sign. This means that we are in user mode and cannot really execute configuration commands. Can only really issue show commands. That's about it. In order for us to have access to our configuration commands, we need to enter privileged exec mode. To do that, we just simply type enable, or EN for short. I will show you both ways. And as you can see, we go from a greater than sign to a hashtag or pound sign. This means that we are in privileged exec mode. Now, in order for us to actually execute commands like create VLANs, go into our interfaces, assign a host name to our switches, we need to enter global configuration mode. And to do that, we just type in configure terminal. But sometimes when you enter in a long string of commands, it can be a little much. So Cisco IOS actually allows you to autocomplete commands by pressing tab, as you saw there. And if I type in T and then tab, it'll autocomplete to terminal. There are also shortcuts to these commands. So I can just type in conf T and I'll still enter global configuration mode. As you can see here, switch parentheses config, which means we are in global configuration mode. Now, let's go ahead and change the host name of the switch for better reference for our topology. So we just type in host name and then SW1. And as you can see, we went from switch to SW1. Now we're going to go ahead and create our VLANs. We just type in VLAN and then let's create VLAN 10 first. So we'll do 10. We are now in VLAN configuration mode, as you can see here. And now I'm going to name this VLAN the admin VLAN. As you can see, name space admin. Hit enter. And now we're going to create VLAN 20. So we're basically going to do the same thing we did for VLAN 10. So VLAN 20, name, and we're just going to change the name and name it finance. Now let's check our VLAN configurations. So if we type in end in any interface configuration mode, we will automatically always go back to privileged exec mode. And this is where we can issue some show commands to verify our configurations. So to verify our VLAN configurations, one command you're going to be using a lot is the show VLAN brief. If we type in show VLAN and then brief, as you can see, our VLANs have been created. Under the VLAN column, you'll see a VLAN ID of 10 and 20, and then the name of the VLAN will be adjacent to that. So as you can see, our admin and our finance VLAN have been created. Now we just need to assign the ports like F0/1 and F0/2 to VLAN 10 and F0/3 and F0/4 to VLAN 20. Let's go ahead and do that now. So if we type in conf T, global configuration mode, now we can type in interface and then fast Ethernet 0/1, but again, sometimes that can be a little bit long. And as you can see, I pressed enter and now we are in interface configuration mode for 0/1. Sometimes typing all that out can be a bit tedious. So if you just type in just int for int and then F0/1, that'll also suffice. We are still in interface configuration mode for F0/1. Now, in order for us to assign this to a VLAN, it needs to be configured as an access port. Now, an access port carries traffic for just one VLAN. Now keep that in mind because as we continue through the video, that's going to be important. So to do this, all we need to do is type in switch port mode access, or we can just type in switch mode ACK. Either one works. You can either take the auto completion or the shortcut route for the command. Either one works. It's all preference. And now that we have the F0/1 configured as an access port, now we could have it be assigned to VLAN 10. And to do that, we can just do switch port access VLAN 10 or switch ACK VLAN 10. Either one works. So to verify our configurations, let's go back to privilege exec mode and issue the same show VLAN brief command. But here I'm going to show you the shorter version of that. Show VLAN and then brief. And as you can see, F0/1 went from being in the default VLAN of 1, and now it's associated with VLAN 10, the admin VLAN. Now let's go ahead and do the same thing for F0/2. We're going to have it be associated with VLAN 10. So we go to global configuration mode, interface F0/2, and now we're going to assign it to VLAN 10 and have it be an access port. Switch mode ACK, switch ACK VLAN 10. And now let's go back into privilege exec mode and do show VLAN brief. And as you can see, F0/1 and F0/2 are now associated with VLAN 10, the admin VLAN. Another show command we can issue is the show interface status, or show int status for short. And as you can see here, you can also verify that F0/1 and F0/2 are associated with VLAN 10. Another show command that you can use, that you're definitely going to use a lot as we dive deeper into trunk ports, is the show interface, and then now we're going to single out a specific interface. So we can do fast Ethernet 0/1, and then after that we're going to do switch port. Again, these strings of commands can be long, so we can always shorten it. So we'll type all this out with a shorter version. So show int F0/1 switch port. Notice how much more shorter and condensed it is. So when we issue this command, we can see that it's an access port because we administratively set it as an access port, and its access mode VLAN is going to be VLAN 10. And we can issue the same command with F0/2. By the way, how I was able to get that command back up is by simply pressing the up key. If I press the down key, it'll disappear. If I press the up key, it'll show the previous command. If I press up again, it'll show F0/1. And then if I press down from there, it'll show F0/2. So another way you can go back, if you have to reuse the same command or do the same command but for a different interface, you can just press the up arrow key and it'll bring you back to your previous commands that you used. Now let's go ahead and configure PC5 and PC6 to be configured as an access port and be associated with VLAN 20. We're really going to do the same thing that we did for PC1 and 2. However, I'm going to show you a different way of assigning them as access ports and having them be assigned to a VLAN. So instead of going into each interface individually, since they're both going to have the same configurations, we can enter a range of interfaces. Again, since they're going to have the same configurations and be associated with the same VLAN, instead of going to each individual switch port, we can do a range of it. And I'll show you now. So we enter global configuration mode, and then instead of doing interface F0/1, we do interface range. And then we do fast Ethernet 0/3 through 4. Or we can do int for interface range F0/3 through 4. See how much condensed it is? Again, all preference. And now we can have it be administratively assigned as an access port and then have it be associated with VLAN 20. So we're going to issue the same commands that we have been with VLAN 10. So switch mode ACK, switch ACK VLAN 20. And then now when we do show VLAN brief, we can see that now F0/3 and F0/4 are associated with the finance VLAN, VLAN 20, way faster than what we did for VLAN 10, PCs 1 and 2. Instead of going into each individual interface, we can go into a range of them to make it way faster, way simpler. So before moving on, I want to quickly go over everything that we just did. The first thing I want to point out are access ports. Access ports carry traffic for just one VLAN, and that is important to remember for when we get into the trunk ports and the native VLAN. So for now, just remember that access ports carry traffic for one VLAN. Now, we configured PCs 1 and 2 to be in VLAN 10 and the switch ports that they're connected to be configured as access ports. Same thing with PCs 5 and 6. PCs 5 and 6 belong to VLAN 20 and the switch ports that they're connected to are configured as access ports. Now, PCs 1 and 2, since they belong in the same VLAN and have the same IP parameters, they should be able to ping each other. Same things with PCs 5 and 6. Let's go ahead and test that now to verify our configurations. So I will issue a ping from PC2 to PC1. As you can see, the pings succeed. Let's go over and do the same thing with PC5 to PC6. As you can see, the pings succeed as well. However, one thing to note is that PCs 1 or PCs 2 will not be able to ping PC5 or PC6 because by default, VLANs cannot communicate with each other. Let's take a gander at switch 2. Now, according to this topology, switch 2 is going to have the same configurations that we just did with switch 1 because switch 2 is going to have a VLAN 10, the admin VLAN, and it's going to have a VLAN 20, the finance VLAN. And PCs 3 and 4 are going to be associated with VLAN 10, and the switch ports that they're connected to are going to be configured as access ports. Same thing with PCs 7 and 8. They're going to be associated with VLAN 20, and the switch ports that they're connected to are going to be configured as access ports. So to speed up the video, you can follow along. I'm going to configure switch 2, and you can follow along with me. But if you need to, pause the video. So right now, I'm going to go into switch 2 and configure it. Change the host name to switch 2. We're going to create VLAN 10, name it the admin VLAN, VLAN 20, name it the finance VLAN. Then we're going to go into interface range F0/1 through 2, switch mode ACK, switch ACK, VLAN 10, and then we're going to go into interface range 3 through 4, switch mode ACK, switch ACK, VLAN 20. Now let's confirm our configurations. Okay, F0/3 and 4, finance VLAN, F0/1 and 2, and the admin VLAN. And we can do a show in status. Yep. So our configurations are basically done on this switch. Now, to further test this, let's do the same verification that we did for switch 1. So let's have PC3 ping PC4. Let's check to see if our IP configurations are done. So that's done for PC3 and PC4. Okay. So now let's go ahead and ping PC3 from PC4 since we're already here. Ping 192.168.1.3. Ping succeed. Now let's go into PC7 and ping PC8. So we'll do ping 192.168.2.4. and the ping succeed. And likewise with switch 1, PCs 3 and 4 will not be able to communicate with PCs 7 and 8 because they're on different VLANs, and by default, VLANs cannot communicate with each other. Now that switch 2 is configured, let's see if we can issue a ping to PC 1 or 2 from PC 4. Because since now both switches are configured with the same VLANs, and these 4 computers are in the same VLAN, in the same subnet, they should be able to ping each other, right? Let's test this. We're going to issue a ping from PC4 to PC1. The ping fails. Let's try to ping PC5 or PC6 from PC8. Let's see if that works. The ping from PC8 to PC5 fails. Why is this happening? If you guessed that the issue lies between the link between the 2 switches, then you are absolutely correct. Now, remember when I said that access ports carry traffic for just one VLAN? That's exactly where the problem lies. The link between the 2 switches are configured to be access ports, which carry traffic for one VLAN. So if the link between the two switches are configured to carry traffic for one VLAN, how is it going to carry traffic for both VLAN 10 and VLAN 20? Now this is where the concept of trunking comes into play. When you have VLANs in your network with other switches connected to it, the ports that connect the switches must be configured as trunk ports in order to forward traffic between them. The way it works is through a process called VLAN tagging by way of the IEEE 802.1q trunking protocol, which means that the sending switch adds a special header to the Ethernet frame before sending it out on the configured trunk. This additional header adds a VLAN ID field to the Ethernet frame so that the switch that sent the frame can associate that frame with a specific VLAN, and the switch receiving the frame can identify which VLAN that frame belongs to. So to summarize, 802.1q trunking allows switches in a network to carry traffic for multiple VLANs over a single link by adding an additional header to the Ethernet frame. This additional header includes the VLAN ID that the frame is associated with. So trunk ports, when compared to access ports, carry traffic for multiple VLANs. So access ports carry traffic for just one VLAN, whereas trunk ports carry traffic for multiple VLANs. Before moving on, I want to explain two trunking protocols that you will or have read about in your studies, VTP and DTP. I will cover VTP or VLAN trunking protocol first because the current CCNA blueprint ignores VTP, but regardless, VTP does have a bit of an impact on Catalyst series switches. And the way VTP works is you have one switch that acts as the VTP server, and then other switches connected to it will be the VTP clients. You only have to configure VLANs on the VTP server because the VTP clients will get the VLAN configurations from the VTP server. However, it's important to note that you cannot change any VTP settings that is connected to a production environment LAN, because you can mess up and possibly delete real VLAN configurations on a production environment switch, which can be very scary. So do not plug in any lab switches to a production environment switch and mess around with VTP, because it can get really messy really fast. Newer switches today actually default to disabling VTP, or in global configuration mode, we can issue the VTP mode transparent command to manually disable it. Doing so will have the switch prevent itself from learning or advertising VLAN configurations. So the only VTP configuration that we're going to do on these switches is actually disabling it. That's really it. We're not going to do any VTP server or client configurations because the current CCNA blueprint does not cover it. So there's no need to do it. We'll start with switch 1. We'll go to switch 1 and we'll enter the CLI and go to global configuration mode and enter VTP mode transparent. And as you can see, it is now set to transparent mode. We're going to do the same thing on switch 2. Now, both switch 1 and switch 2 have VTP disabled, so they will not learn or advertise any VLAN configurations. Now let's move on to DTP, or Dynamic Trunking Protocol. DTP allows our switches to dynamically send and learn about trunking negotiation messages. Let's take a look at this further so you can get a better idea, and we'll start with switch 1. If we go into switch 1 and enter privilege exec mode, we can enter the same command that we did before to single out interfaces to see the administrative and operational modes. And to do that, it's the show interface G0/1 because that is the interface that's connected with switch 2, G0/1, and then switch port. As you can see, the administrative mode is set to dynamic auto. And if we head over to switch 2 and do the same thing, you can see that its administrative mode is set to dynamic auto as well. What does this mean? In dynamic trunking protocol, dynamic auto means that these switches will sit and wait until they receive trunking negotiation messages. And the reason why trunking isn't occurring right now is because both of these switches are sitting and waiting for trunking negotiation messages to be received. And if both of them are passively waiting for that, trunking is not going to occur. So by default, they're going to be access ports. So that's why trunking is not happening on our topology right here. So let's go ahead and configure trunking on our network here. So if we're going to use DTP for trunking, one end needs to be configured as dynamic desirable. Just like how we went into our switch ports to assign them as access ports for our computers, we need to go into gig 0/1 on either switch, and at least one end needs to be configured as dynamic desirable. So we'll do that with switch 1. So go to switch 1, and then we'll go to global configuration mode and then interface configuration mode for gig 0/1. And instead of doing switch port mode access like how we did before to configure our PCs as access ports, we're going to want to do switch port mode dynamic desirable. And what's going to happen is once you execute the command, you're going to see the link go down for a little bit because trunking is being negotiated. So if we go back to interface or privilege exec mode, and enter the same show command that we did before for our gig 0/1 interface, now you can see the administrative mode has been changed to dynamic desirable, and now the operational mode is set to trunk rather than static access before when it was configured as a dynamic auto administrative mode. So if we scroll back up, you can see dynamic auto, static access. And now it is dynamic desirable, trunk. Now let's go over to switch 2 and see how switch 2 reacted to these changes. So let's go and issue the same show command we did to single out G0/1. And as you can see, even though it is set as dynamic auto, its operational mode will be trunk because, again, dynamic auto essentially tells this switch to sit and wait for trunking negotiation messages. And so since we configured switch 1 to be dynamic desirable, it's going to send out the trunking negotiation, and switch 2 is going to accept it, and then trunking will occur. Now let's go ahead and issue some pings between our computers in the same VLAN. So let's ping PC1 from PC4, like how we did before, and let's see if the pings will now succeed. So from PC4, let's issue a ping to PC1. And as you can see, the ping succeed because we configured trunking. Let's test the same thing for VLAN 20. So from PC5, let's ping PC8. And as you can see, the pings succeed. Now let's look at another way to configure trunking on either switch's gig 0/1 interface with another command. Let's go over to switch 1. If we go to privilege exec mode and then global configuration mode, let's go into switch 1's gig 0/1 interface. And instead of doing switch mode dynamic desirable, we're just going to do switch port mode trunk. Simple as that. And now if we go back to privilege exec mode and do the same show command we've been doing, show int gig 0/1 switch port, you can see the administrative mode has now been set to trunk, not dynamic desirable. And if we go over to switch 2, we can verify that it is still receiving trunking negotiations even though it is still set to dynamic auto. Operational mode is still set to trunk. And to further confirm this, let's issue pings again. So I'll go back to PC4 and issue the same ping, and as you can see, I can still ping PC1. And we'll go over to PC5 to ping PC8 again, and there you go. Trunking is still occurring. Switch 2 is still receiving negotiations from switch 1, even though we didn't configure it with dynamic desirable. It is still in trunk mode. Another way to confirm your trunking configurations is with another show command called the show interfaces trunk command. And with this command, you can get a lot of details about your trunk ports, like the type of encapsulation it's using, whether it's using ISL or 802.1q, the status, whether it's trunking or not, as well as the native VLAN, which we are about to get into here in a moment. We can do the same thing on switch 2 and issue the same show interface trunk command. And as you can see, the mode is set to auto because we didn't change the trunking on gig 0/1 on switch 2. So it's still set to dynamic auto, but it's still trunking because it's receiving negotiations from switch 1. Now let's configure both ends to trunk and disable DTP negotiations. If you choose to configure both ends to just trunk and not use DTP, DTP negotiations can still occur if you choose not to disable it. We can disable DTP negotiations by going into each switch's gig 0/1 interface and use the command switch port no negotiate. So since we're already in switch 1, we're going to go into interface gig 0/1 and we're going to configure it to trunk. And now what we're going to do is switch port no negotiate. So we're going to disable DTP. And on switch 1, we're going to do the same thing, because we already have it set to trunking. And so as you can see, both ends are trunk. Operational mode is trunk. Switch 2, we can check the same show command, and you'll see the administrative mode is set to trunk and the operational mode is set to trunk. So now we have both ends trunking and DTP negotiations disabled. Also, don't forget that we disabled VTP as well by using the VTP mode transparent command in global configuration mode. I must say that this can cause misconfigured 802.1q trunking because, for example, one end can be administratively set to trunk and disable DTP, and the other end uses dynamic desirable, which relies on DTP. So switch 2 could be configured to be administratively set to trunk, and switch 1 could use dynamic desirable, and trunking will not be able to occur because we disabled negotiations on both switches. So just be mindful when you are configuring trunk ports and disabling DTP and having one end be configured to rely on DTP. And finally, I want to bring up an important topic that is defined in 802.1q, and that is the native VLAN. 802.1q defines the native VLAN as the only VLAN to traverse the trunk without a VLAN tag. So both switches, when sending a frame assigned to its native VLAN, will not add an 802.1q header. So with that, both switches know that untagged frames mean that the frame is part of the native VLAN, and treat untagged frames as being part of the native VLAN. Let's demonstrate this first by analyzing traffic that occurs when PCs in VLAN 10 on switch 1, so PCs 1 and 2, send traffic to PCs in VLAN 10 on switch 2, so PCs 3 and 4, assuming the native VLAN is defaulted to 1. I want to show this first so I can demonstrate the 802.1q header that is added to the Ethernet frame when VLAN traffic traverses the trunk versus when untagged frames traverse the trunk. Now let's begin the simulation so we can start analyzing the traffic between the VLANs. We'll begin by pressing simulation on the bottom right, and then edit filters, and then select show all/none, and then just select ICMP. We're going to ping PC4 from PC2, so click on PC2, and then go to command prompt, and then now we're going to issue the ping. Now what we're going to do is analyze the frame when switch 1 receives it from PC2 from F0/2. So we can see the frame right here, and on the left under in layers we can see the frame enter F0/2 from PC2, and then the switch adds the 802.1q header destined for PC4 on VLAN 10, which is what the 802.1q header is, for switch 2. What's cool is that Packet Tracer gives a really great explanation on how it's going to forward the frame based on our configurations that we just did. So if we click on the layer 2 header, we can see the outgoing port is a trunk port and the incoming port VLAN number is allowed in the trunk. Switch sends out the frame to that port. Let's continue to analyze the traffic even further. So it arrives to switch 2. And as you can see, the 802.1q header is there, and switch 2 is going to strip the header because it knows which VLAN it belongs to, and that way it can send it to the correct MAC address. So as we can see here, now you can see that there is no 802.1q header because switch 2 removed it, because it knows that this frame belongs to VLAN 10, and then it analyzes the destination MAC address, checks its MAC address table, and forwards and filters the frame out of the correct interface. Now let's configure both switches to have VLAN 20 become the native VLAN on the trunk. Let's start with switch 1. And we'll first have to go into its gig 0/1 interface. So enter global configuration mode, interface configuration mode for gig 0/1. And we need to issue the following command: switch port trunk native VLAN 20. We need to make sure to do the same thing on switch 2 so we can avoid a native VLAN mismatch. So let's go ahead and do the same thing. If we go back to privilege exec mode and do the show int g0/1 switch port command, we can now see that our trunking native mode is now set to VLAN 20, the finance VLAN. Before, if you didn't notice, the trunking native VLAN was always set to 1. Let's confirm this on switch 1 as well. And as you can see, the trunking native VLAN is also set to the finance VLAN. So let's see what happens when we issue a ping from PC5 to PC8. Let's see how switch 1 and switch 2 behave when it receives and forwards untagged frames. So let's go back to simulation mode. We'll reset the simulation, go over to PC5 and issue a ping to PC8. And when we go over here, let's see how the frame is when switch 1 receives it. It will not add an 802.1q header. As you can see here, in the previous example, switch 1 adds the 802.1q header to forward out of the trunk port. But switches treat untagged frames as being part of the native VLAN. So when it traverses the trunk and switch 2 receives it, the same thing is going to happen. No VLAN tag is going to be added. So to quickly summarize, access ports carry traffic for one VLAN, trunk ports carries traffic for multiple VLANs, and the native VLAN is the only VLAN to traverse the trunk without a VLAN tag. We covered a ton of information in this video about implementing VLANs, and I hope this lab video has been helpful. The next video will most likely be about spanning tree because it is what I am studying at the moment. Again, I want to thank you all for watching my video, and I'll see you in the next one.